Hello, and welcome to this presentation of our work, Hyperbolic Unsupervised Anomalous Sound Detection. First, a brief summary of our findings today. We'll see that hyperbolic-based embeddings organize in ways that produce performant, low-dimensional detectors for anomalous sound. A little background first. Automatic anomaly detection is expected to bring crucial benefits to modern industry by automating the tedious task of machine monitoring. In this context, the audio modality is particularly appealing with cheap sensors and allowing monitoring without line of sight. Today, we'll be looking at unsupervised approaches. In most industrial contexts, those are the only viable ones, as collecting anomalous samples is difficult to impossible. We'll be investigating the usefulness of hyperbolic representation in the context of surrogate task methods. Just a brief reminder, surrogate task methods consist in finding a surrogate classification task for the available normal data. And that means we're expecting the normal data to be labeled in some manner. For example, if we're trying to build an anomaly detection system for fans, we could consider building a classifier to determine the model of the fan or its operating speed or any other attribute that we're able to collect. Once we train the corresponding classifier, we'll use the internal representations learned by the classifier to make a determination on the condition of unseen data. So this final step is what we're seeing on the right here. We have this pre-trained classifier, and we can actually look at the embeddings distribution for normal training audio samples. Once we receive an unseen audio sample, we can check where its embedding lands relatively to the others and hopefully build some kind of anomaly detection based on those characteristics. Moving on to this idea of hyperbolic representation. In mathematical terms, hyperbolic geometry is defined as manifolds with constant negative curvatures, which contrasts with old regular Euclidean geometry where we have zero curvature. Hyperbolic geometry has, in prior research, found to have a couple of interesting properties. First, it naturally encodes hierarchical data, because the same way that the number of nodes per depth in trees grows exponentially with the distance to the head node, we find that local volume grows exponentially with distance to the origin in hyperbolic space, something that is not true for Euclidean spaces. And a more recent finding is that when looking at the geometrical distribution of embeddings for classification in an hyperbolic sense, it has been found that some notion of classification confidence correlates quite strongly with a very distance to the origin. Here, as a graphical illustration, we see a projection of a 2D hyperbolic space the same way we would have to look at a map as a projection of the Earth on a slide. And here we see the origin and the edge of the hyperbolic space, meaning this is technically infinity. And this encoding of certainty would be this distance to the origin here. Another consideration that would be important is that while there are some notions of hyperplanes and distance in hyperbolic space, they are different from the same one in Euclidean space. And that's really what makes the difference between working with hyperbolic representation versus Euclidean representation, as we'll see in a minute. Here in the paper, first we looked at two baseline systems. One is a relatively straightforward Euclidean system with input features going through a backbone network, producing hidden Euclidean embeddings that are then fed to a linear layer, generating logits. And then this is all trained end-to-end by cross-entropy loss. What you need to keep in mind here is why are we characterizing those embeddings as Euclidean? Is because a linear layer essentially parameterizes hyperplanes in the Euclidean sense. And so that's why we can retroactively interpret those embeddings as being in Euclidean coordinates. For completeness, we also added an arc-phase system due to the propriety of that approach in recent research. And the only difference here is that arc-phase embeddings are optimized in a slightly different way. They try to have some sense of maximization of the angular margin between the location of the embeddings of various classes. Still, we can call them Euclidean because at the end of the day, we still perform linear classification in the Euclidean sense at the end. Here, our proposed system today is the hyperbolic system here. So as we see, it's again just a small modification of the baseline Euclidean system. And what will change here is that we have to perform a one-to-one mapping from Euclidean coordinates to hyperbolic coordinates. And then we'll train an hyperbolic linear classifier here. And so the reason why we can call those embeddings hyperbolic and this is an hyperbolic classifier is because we're optimizing hyperplanes in the hyperbolic sense this time. Once those various classifiers have been trained, what's left for us is to define some notion that we'll use to measure anomaly. First, this is the baseline scores for surrogate task methods proposed in the DCASE 2022 task 2 documentation. And this is essentially assuming we do have also attributes for unseen data, meaning when we're presenting an unseen data, for example, we could imagine that we have the model number of the machine we're trying to monitor. We'd be looking at how well it predicted the correct machine model for that unseen data versus predicting an incorrect machine model. Today, adding this hyperbolic notion of uncertainty, we wonder if correlating classification uncertainty with anomaly would be performant. And so we also built a new anomaly score based on assessing the distance to the origin and using that to distinguish anomalous samples from normal samples. And finally, considering those two notions of anomaly above are reasonable in their own right, we look at the idea of ensembling them by building a combination score, with the only caveat that we have to perform some transformation as they are not on the same scale. And those transformations result in them being mapped to between 0 and 1. Finally, we have the result using the DCASE 2022 task 2 benchmark. On the validation set, once we look at systems trained for 2-dimensional embeddings and 128-dimensional embeddings, we find that, unfortunately, the distance to the origin alone is not a very effective anomaly detecting score. However, it is combined quite advantageously with the original baseline score. And furthermore, we can observe that for both 2-dimensional systems and 120-dimensional systems, the hyperbolic representation scores best. Moving to the evaluation set, we find interesting observation, like the fact that while hyperbolic systems generalize quite well in 2-dimension compared to their Euclidean counterpart. That is not true in the 128-dimensional case. However, crucially, the ensemble approach in 2-dimension tops the chart, both among 2-dimensional systems, but also across all baselines and systems. Just to give us what we believe is a good intuition for that, we generally assumed as a foundation of this paper that hyperbolic geometry will allow data to organize more effectively in the context of finding anomalous data versus normal data. And in this context, the 2-dimensional hyperbolic systems are just more powerful and robust than their Euclidean counterparts. At the same time, looking at the lower generalization of the 128-dimensional system, that could be also consistent due to the fact that if indeed that geometry is more effective, we could reasonably expect an hyperbolic system to start overfitting to the training data at a lower dimension than for an Euclidean counterpart, and as such, experience a loss of generalization more rapid as the dimension of the embeddings is increased. Finally, let's look at just a graphical illustration of those scores. So here we're looking at the embeddings for the validation data that is provided in the challenge. And for all those machine types, fan, sliders, we have 3 models that we tried to classify. And so here, comparing the embeddings that were generated based on normal data versus the embeddings that were generated based on anomalous data, we observe behaviors that are consistent with our anomaly scores. First, we see that anomalous embeddings do tend to live closer to the origin than normal ones. And in other cases, we do see the embeddings move from their correct class far closer to an incorrect class. Also, what we find interesting is that when looking at the distribution of anomalous embeddings, which is just generally broader than their normal counterpart, they tend to organize quite clearly in a manner that is close to the origin, rather than moving along the edges of the space. As such, we feel further comforted in the reasonableness of our approach today, and see the use of hyperbolic geometry as worthy of further exploration in future research. All right. I thank you for your attention today. I hope you enjoyed this presentation. If you have any question, please don't hesitate to reach out to us in person at the conference, through Slack or by email. Thank you again. Bye.